Welcome to my classes of Fundamentals of Electrical Circuits. We were into theorems and we saw that there are very easy adaptations or adoption of Thevenin's and Norton's theorem. We also saw that we can make very good tools out of superposition. No, not superposition, essentially source transformation. And there are a few concepts which can be easily employed at several junctures. So in this session, we'll be consolidating many of them, and we'll also be trying to see if superposition helps. Okay, so sometimes superposition does help, and so we'll be looking at superposition also as is applicable to problem number 1. Okay, so when we observe the contents of this problem, we see that on the periphery we are having 1 ampere source, and it is in series with a 5 ohm resistor which can be discarded. And all through we see that if the 8 volt source is shorted, which is applicable to superposition, then we have a free path for the 1 ampere current to flow, which comes out from the 1 ampere source. So this is the idea that we are going to follow through. So now we have a look at the two 8 volt sources. We see that there is some kind of an identical nature with respect to each of them, or a sort of a symmetry. And so let's read what the problem is and then go thereafter through the problem. The figure showed the current I in amperes. So obviously one part is already solved, in the sense that the 1 ampere now releases the current through it, and it flows all the way if the 8 volt source is shorted. And this happens when we are adopting superposition theorem. So we see that now the current is equal to 1 amps, but it's in the reverse direction, so it's minus 1. So now let us look at both the 8 volt sources in tandem together. So what do we see? When you look at the upper 8 volt source, we see that there is a 1 ohm resistor in series with it. Then thereafter there are 3 1 ohm resistors all parallel together and joining at A. A and A happen to be the same point. And on the other hand, if you convert it into a current source, adopting source transformation, then we are having an 8 ampere now diverging through 4 1 ohms, and 2 1 ohms are connected together to give rise to a total current flow through AAA. And if you observe the middle 8 volt source, the picture is similar. There's 1 ohm resistor in series. Thereafter, the current diverges through 3 equal paths, and 2 paths are connected together at AA dash for the current to flow. And these currents are going to flow in opposite direction. Here also you can use source transformation, and here also you see that there is an equal amount of current, but flowing between A and A, but they are in opposite direction because of the direction sense of the 2 voltage sources. So they cancel each other, and so the value is equal to 1 amps. So all these things you can simply observe from the problem and make a mental note and come to the conclusion that the current is only equal to 1 amps. Moving on to problem number 2, which has been taken in from the Indian Engineering Service Examination for junior engineers. We see a very simple problem, in the sense that there are 2 sources, one 10 amps and another 5 amps, and there is a voltage V1 marked across 1 ohm. So this could be what we have to find out. And also we notice that though there's a 2 ohm resistor at the top, we have 4 ohms in parallel with respect to each other, and in parallel to 5 amps. So this might give rise to a source transformation, which might make things easier. So what is asked is, for the circuit shown below, as is guessed, the voltage V1 needs to be found out. So what do we have here? So we cannot disturb the left side. The 10 amp source on the left side had better be left as it is. So we start processing from the right end. So we see that this now 5 amps source with 4 and 4 in parallel gives rise to a voltage source, with the bottom terminal as positive, and the voltage is equal to 5 into 2, 10 volts. And now these 2 and 2 ohms resistors become in series. So now we are having a 4 ohm resistor, which gives rise to another current source, 10 by 4, and now we are having the 4 ohm resistor in parallel to the original 1 ohm resistor, across which the voltage needs to be found out. So what do we see? We see that there are 2 current sources, one moving up, one pushing current upward, the other pushing current downward. So the net effect is 10 minus 10 by 4, which is equal to 30 by 4 being divided amongst the 4 ohm resistor and the 1 ohm resistor, okay, and the current through the 1 ohm resistor crosses the voltage, so into 1, okay, so it's going to be 30 by 4 into 4 by 5, which is equal to 6 ampere, which is also equal to 6 volts, okay. So easily we can do this particular problem, and we can come to a little more difficult problem, which is shown in 3, but it is very indicative and very informative, as also very much useful for the general scheme of things, okay. So we see, I suppose we see a complex structure with a voltage source E at the left end, not the value not given, and a 4 amps source on the other end, and then there is a network of 4 and 4 ohms on the voltage side and 2 and 2 ohms on the current source side, and in between we are having an unknown resistor R and a 2 ohm resistor, okay. So what is required is, okay, what else is given in the circuit figure when R equal to 0, okay. What is the situation when R equal to 0? It talks about a short circuit. It also talks about the Norton current, okay. The current is equal to 10 amps. So Norton current is given, okay. Now so we can process things from the point of view of a Thevenin's or a Norton's equivalent, because Norton and Thevenin equivalents are duals with respect to each other, okay. So what is asked? Find the value of R for which it absorbs maximum power. So when you are asked about maximum power, immediately Thevenin's equivalent should come to the mind, and that's going to be the resistance here, not impedance, okay. When you are having an AC circuit, it's going to be impedance, okay. So now we move on to finding the overall resistance. So we look on either sides of resistor R, okay, which is shorted to obtain the just to obtain the Norton's current, okay. So to obtain the total Thevenin's resistance. So on the while we short circuit the voltage source and open circuit the current source. So on the left side you see that there is a 2 ohms in series with a 4 ohm and 4 ohm parallel, or with another 2 ohms. So we are having 4 ohms on the left side. On the right side of R we are having 2 and 2, because the current source has been removed, 2 and 2 4, okay. So 4 and 4 on either sides gives rise to Thevenin's resistance, which absorbs maximum power as equal to 2 ohms, okay. So that portion is solved. Now we move on to what else is asked. Find the value of E, okay. So under this circumstance we see that we can find out the value E as the voltage across the resistors, okay. So now we are having we are seeing that since R is shorted, there's a current, and the current flow of is equal to 10 amps is flowing through it. We see that there are two contributions. One is from E, the voltage of the value of which we don't know, and another is of 4 amps which we know, okay. So if R is shorted, the 4 amps split equally between the 2 ohms, and so we are having a 2 ampere contribution from the current source side, okay. So the rest is all going to flow from E, okay. So we are having 8 ohms coming there and creating a voltage drop across 2 ohms as equal to 16 volts, because it is shorted, okay. So this 16 volts is applicable also across the 4 ohms, which now takes 4 amps, okay, consequently, okay. So together we are now having 12 amps flowing through the 4 ohms connected to E, okay. So now 12 amps through 4 ohms and 8 amps through 2 ohms will together create the voltage E as given by 12 to the 48 plus 8 to the 16, that's equal to 64 volts, okay. So that takes care of B, solution of B. This was a big question that came for gate examinations in the earlier days, when concept questions were asked with bigger marks and with a solution methods to be identified, okay. So finally we need to find out in C, find V2 when R equal to open circuit. So now we are back to the earlier concept that that R can be open, then it's a Thevenin's equivalent, or R can be closed when it's shorted, it's a Norton's equivalent, which are the same, which happen to be the same, okay. So now we are having, what do we have here now? So now we know the value of E, which is equal to 64 volts, and we see that there is a 4 ohm resistor in series with it. So together you can give rise to a current source of 16 amps, okay, and the 4 ohms will adhere on to the other 4 ohms, and we are having a 2 ohms resistors there. And now the network structure is very interesting in the sense that we are having an identical structure when looked at it, okay. So we are having 2 ohms on one side, 2 ohms on the other side because of the that which is going to be which is parallel to the current source, and in between you are having, because of the open circuit which is R now, we are having 4 ohms here. Okay, so 2 plus 2, 4 ohms here. So what is the situation? We are seeing that both 16 amps and 4 amps see the same structure. Okay, or in other words, in total we see that only 12 amps now flows from the left side source, because 16 minus 4, the impact is the same. So 16 minus 4, only 12 amps flows from the left side. Okay, and it flows through the or else or in other words, the effects get cancelled out. So in effect, there's only 12 amps flowing from the left side. Okay, so 12 amps flowing through the 2 plus 2 ohms resistor is the same as equal to 12 into 2 by 2 plus 2 plus 2, that is 8. Okay, and that is the other current source is removed, because we have only one current source which is equal to 12 amps. Okay, so 12 into 2 by 8. Okay, and then you have to multiply it also by 2 to get the voltage across it as V2. So we are having 6 volts as the answer. Okay, so many concepts have been joined together here, and as we want, we can we need not use even pen and paper. Just by looking at things, we can try to get such an understanding and do the problems with an understanding, which is what is called as intuition. Okay, moving on to problem number 4. Again, it's a gate question, but it looks a little complex. But when you are seeing a complex situation, immediately realize that there must be something or the other which is good in it. Okay, and of course, I'm reading the question first, because it doesn't make a big difference. It is asking us to find out I2. Okay, where is I2? I2 is at the center of everything. That is, it is the current that comes out from the 2 volt source. Okay, with the direction as shown, and in series with it we are having 2 ohms. But on either sides of this central situation, we are seeing that there is a network of 1 ohm and 1 ohm. Okay, so on either side, so we are actually having a Wheatstone structure if looked at from the 1 amp source on the other side, as also if looked at from the 4 volt. Okay, 4 volt or 4 volt in parallel with 4 ohm or whatever. Okay, side. Okay, so both these sources now give rise to no current through the central center of the Wheatstone structure. Okay, I suppose this is clear. Okay, so we are using the Wheatstone principle here, and we realize that if to find out I2, 1 ampere has no contribution. The 1 amp source has no contribution, nor does the 4 volt source have any contribution, because the 4 volt source you can convert it into whatsoever current source or whatever, but of course it's a 4 volt. Okay, so it has no it will create no ripples in the center of the Wheatstone bridge. Okay, so now we have only 2 volt source. Okay, so we have already applied superposition, though superposition is only applied for a particular purpose. What is that particular purpose? Okay, we are trying to find out the network structure through which the current emerging from 2 volt flows. Okay, so 1 ampere source is shorted, and now 4 volt source is the 1 ampere source is opened, and the 4 volt source is shorted. So what do we have? We now have a very interesting situation where we see that there's the current emerging from 2 volt flows through 2 ohms, and then it flows through 2 parallel 1 ohm resistors, and then there is another parallel 1 ohm resistors, that is the paralleling is through the 4 volt source. Okay, so in total we are going to have 2 volt source and a 2 ohm resistor, and we are having half and half resistors. There is 1 and 1 parallel to create a half, and then in series with the other 1 and 1 in parallel, so another half. So in total we are having 3 ohms resistors. Okay, so 3 ohm. So we see that so we see that it's going to be the same as equal to 2 by 3. Okay, so 2 volts divided by 3. Okay, that gives you the current I2. Okay, I hope the concept that both superposition and Wheatstone has been used to our advantage to solve it without using any pen and paper is made clear to you, wherein the sources are the sources on the left side are removed, and then the voltage source is also used to parallel the resistors, such that we are having 2 1 ohms in parallel first, and then the other pair of 1 ohms in parallel again. So together we are having 1 ohms there. Okay, so that's all that's there for in problem 4. In problem 5, again borrowed from the IEX examination, we see a 5 volt source, a 5 ampere source, and a 1 ohm resistor, which is always going to be destined to carry 5 amps, because we are having, not because 5 amps source is there, but because 5 volt source, 5 volt is the voltage across the 1 ohm resistor. Okay, so please don't make any mistake about the 5 amps, because this 5 amps is now perhaps flowing entirely through the 1 ohm resistor, but that's not the picture. It could be 2 amps, it could be 3 amps, whatever. It could be any kind of ampere source. It could be infinite amps, but still the 1 ohm resistor will carry only 5 by 1, which is 5 amps. Okay, so the value of current I flowing in the 1 ohm resistor in the circuit shown in the figure is 5 amps. Okay, there's no doubt about it, and this is a very important concept that sometimes students make mistakes in. Okay, now we are having a gate question where we see that we are having 6 milliamps, 2 milliamps and 4 volt source. 4 volt source in series with 1 kilo ohms will always give rise to an understanding that it's a possibility that you can have a 4 milliamp source. Okay, that is, you can use source transformation if required. Okay, and now what we have here, we have 3 1 kilo ohms. Okay, so and V0 is there. Perhaps we need to ask, we need to find out V0. Okay, that's exactly what is asked. Consider the circuit shown below and the value of V0 rounded off. Okay, so we need to find out V0. Okay, so how do you start? First, of course, maximum information. What is maximum information? That the 1 kilo ohm connected to both the 6 milliamps and 2 milliamp current sources will carry 8 milliamps, because it has to subscribe to 6 milliamps on to the source at the top and 2 milliamps to the source on the left, on the right side. Okay, so what do we have? So 8 milliamps. Okay, so that's one thing. And another is, of course, now let's look at the left side of the picture. We see that 6 milliamps is coming. Okay, and we are having 8 milliamps moving out. Okay, there's a junction shown with a star which is 5 which has 5 prongs. Okay, one is, of course, the 6 milliamps which is coming from the top, 8 milliamps which is leaving from the side, and 4 volt with 1 kilo ohms in series. Now it's a 4 milliamp, so that's also joining there. And then we are having two 1 kilo ohms. Okay, because when the source is converted into a voltage source is converted into a current source, we are having another 1 kilo ohms in parallel. Okay, now these two 1 kilo ohms are going to share the total current that now results. So what is the total current? 6 is coming in, 4 is coming in, 10. So we are having 10 coming in, and now 8 is leaving. So now you are having 2 milliamps being shared by the 1 kilo ohm resistor. So each one gets 1 milliamp. So it's going to be equal to 1 milliamps into 1 kilo, which is equal to 1 volt. Okay, very simply you can do it, so long as the idea that maximum information, source transformation as and when applicable, all can be utilized and a general picture can be formed with respect to the data given. Okay. Problem 7, we have 3 amps in series with the 1 ohm resistor discarded. Okay, once you discard it, then 3 amps becomes in parallel with another 1 ohm. So you can have, okay, so let's see what is asked. And then we are also having a 1 volt source with a 3 volt source, 1 ohm resistor with 3 volt, and there's a voltage V, which could be what is asked. The value of V in the circuit shown in the given figure is what. Okay, so now, so we can start from, so since V is on the other side, we can start from here. So 3 amps in series with 1 ohm is removed. So 3 amps in parallel with 1 ohm, that becomes a 3 volt source, and the 1 ohm resistor is now added in series. Okay, so now we are having the top portion is positive, the bottom portion is negative. So now we are having 3 and 3, 6 volt. Okay, 6 volt is now opposed by 2 resistors. One is the 1 ohm resistor across which we are having voltage V, and other is the other 1 ohm resistor. So the voltages are shared, so it's going to be equal to 3 volts. Okay, without any doubt we can come to an easy solution for this. Okay, so moving on to problem 8. Again, we see a 1 ampere source in the so this is the advantage of looking at the circuit first and then reading the problem, because we are more or less convinced about whatever is available and how you can transform them to a useful kind of situation. Okay, so 1 ampere, 1 ohm resistor. Okay, 1 ohm resistor again, and then a 2 ohm resistor, and terminals A and A dash. Okay, and the figure shown below, if we connect a source of 2 volts. Okay, so now we are going to add more to the picture. 2 volt with internal resistance of 1 ohm. Okay, so 2 volt and 1 ohm is going to be added. You have to imagine that, okay, without drawing. Okay, with positive terminals at A, then current through R is what. Okay, so now we are having another source, 2 volt and 1 ohm in series. So you can think about a 1 ohm now coming parallel to the resistor R equal to 2 ohms, okay, and creating a 2 by 1 that is equal to a 2 ampere source with which is upwardly mobile, that is the current is pushing upward, okay. So now we are having yeah, so this is the situation, and what is asked in the circuit shown below, if we connected, okay, 2 volt source with resistor 1 amp at A dash with positive terminal at A, then current through R is what, okay. Okay, so now we are having 1 ampere in parallel with 1 ohm. So, 1 ampere source in parallel with 1 ohm, so that can be a 1 voltage source with now to 1 amp 2 ohms, okay. And so now we see, so we have retained R, okay, 2 kilo ohms, 2 ohms we have retained, okay. So from we are now working from the left side, so now we are having a half ampere, that is the half ampere source with 2 ohms in parallel to it. So now we are having 2 ohms and 2 ohms and another 1 ohm. So now these two ohms are parallel with respect to each other. That creates another 1 ohm. Okay. So all these aspects can be joined together in the understanding that in total we are having 2.5 amp, 2 plus half, that is 2.5 ampere. Okay. Now this is divided into the 2 1 ohm resistors that we have recently created, which is equal to 1.25. Now the recently created 1 ohm was obtained as a result of paralleling 2 1 ohms. So again divided by 2. So we are seeing that the answer is equal to 1.25 divided by 2, which is equal to 0.625. Okay. So I'll just repeat a little. We work from the left side. We convert the 1 ampere source to a half ampere source after 2 transformations. First is the current, first is the voltage transformation, and then there's a current transformation. Okay, and so now we are having 2 ohms in parallel. On the other side, we just connected a 2 volt source with 1 ohm. So that was another 2 ampere source with 1 ohm. Okay, so now we are having 2 1 ohms. Okay, so the total current is divided between the 2 1 ohms. Okay, thereafter the 1 ohm that is created out of paralleling to 2 ohms is now again the current is divided into 2. That's all. Okay. So far we could do all these things because we are using Ohm's law, okay, essentially Ohm's law, which is of course a linear situation. Otherwise, you wouldn't be able to do it, okay. So finally coming to one of the problems again in GATE, okay, earlier version, and it is actually supposed to be very tough, but then we'll see how we can easily solve it, okay. So this will be the last of the problems that we are discussing in this section, and we are also trying to be very confident in the sense that any circuit can be transformed to whatever we want, such that we, of course, keeping all the laws intact, we can do them easily, okay. So we are having a situation wherein we are having a voltage E, value not shown, a 4 ohm and 6 ohm on one side connecting to it, as also a 8 ohm and 2 ohms, and then there are 2 bits of 3 ohms connecting to another part of the circuit which has 10 ohms and 5 ohms and an ammeter M1. There's a switch there and empty. Okay, so what is asked is in the circuit of figure, when switch S1 is closed, there's only one switch, so that could be the switch which is closed. So when switch is closed, it's clear that now we are having the 10 ohms and 5 ohms in parallel. Okay, so that's point number 1. The ideal ammeter M1, because it's ideal, okay, it reads 5 amps. So the current flowing through 5 ohms is equal to 5 amps. Okay, what will be the ideal voltmeter M2? What will the ideal voltmeter M2 read when S1 is kept open? So the next situation is when S2 is open, which means that there is a voltmeter which is reading the open circuit voltage. Okay, it's reading the voltage across 10 ohms because through 5 ohms nothing flows, since the voltmeter is considered to be ideal, and so with infinite impedance. Okay, so that's the situation. So let's see. So let's start from the left side. We see that there is a voltage. Okay, so I'm using Thevenin's here because Thevenin's is the best thing that we can use in this context. Okay, so what does Thevenin's tell you? From the left side, where we don't know what is the value of E, it's also said that value of E is not specified. Whatever be the value of E, okay, so that's the situation. So we see that whatever be the value of E, the voltage across PQ as a Thevenin's source is the same as equal to a division of voltage of E between 6 ohms and 4 ohms, as also between 8 ohms and 2 ohms, and the difference between 6 and 8. Okay, so it's obviously the same as equal to, the VTH is the same as equal to 0.2, that is 6 by 10. Okay, and 8 by 10, the difference between them is the same as equal to 2 by 10 or 0.2 times E dash. Okay, so that's point number 1. And the Thevenin's resistance, when you look back, because the source is shorted, that is the E is shorted, we see that now we are having 6 and 4 in parallel through the short. Okay, that is 2.4, and 8 and 2 in parallel, that is 8 to the 16 by 10, 1.6. So 2.4 plus 1.6, 4 ohms. Okay, so now the left side has been completely resolved into a very useful concept of a Thevenin's, wherein we are having 0.2 E as E dash. Okay, I'm just calling it E dash for the time being, and there is a resistor 4 ohms in series with it, a Thevenin's equivalent. Okay, and now we are seeing that this 4 ohms is now going to be in series with another 3 ohms and 3 ohms and a parallel combination of 10 and 5 ohms. Okay, in case number 1. Okay, so case number 1 is the same as equal to having a voltage across the 10 ohm and 5 ohm in parallel as equal to how much is equal to, it's a potential divider there. We are having and the E dash multiplied by the combination of 5 and 10, which is 5 into 2 by 3 or 10 by 3. So E dash into 10 by 3 divided by 10 by 3 plus 10, because the rest constitutes 4 and 3, 7 and 3, 10. Okay, so we so we see that 10 by 3 plus 10. Okay, so we see that this voltage is now equal to E dash by 4. Okay, and this gives rise to, so E dash by 4 by 5 ohms gives rise to a current equal to 5 amps. Okay, so that is that's case number 1. Now we come to case number 2. Okay, so now the circuit switch has been opened. So what do we have now? E dash. So we don't have 5 ohms at all because it's an open circuit. So 10 ohms is now in parallel with is in series with all the other 10 ohms. Okay, so the voltage division is now equal to E dash into 10 by 10 plus 10. Okay, because both are now 10 ohms. Okay, so now the voltage is now E dash by 2, which is double the voltage of which is double the voltage in the earlier case. What about the impedances? The impedances now, it's not 10 and 5 in parallel, it's a simple 10 ohms. Okay, so the impedance is now doubled. Okay, so now so in effect it can be seen that the current is the same, which is equal to 10, which is the same as equal to 5 amps. Okay, so if it is 5 amps, then then we see that the impedance is double. I say so not because of the parallel combination, because earlier we considered only 5, the voltage was across 5 ohms as also 10 ohms, so we consider only 5 ohms. Now the voltage is across 10 ohms. Okay, so we see that the current is also the same, the voltage is doubled, the impedance is doubled, so the current is equal to the same 5 amps. So 5 amps into 10 volts 10 ohms creates a 550 volts drop. Okay, so we have experimented with many kinds of concepts, and I'm hoping that without even I'll be putting them together, but that's enough for the time being, that the concepts are well accepted. Okay, thank you.